The year is 2077. Humanity reached further than ever. Our vessel, the Stardust Drifter, was a marvel. It was designed for deep space. We aimed for the Cygnus X1 region, a place of cosmic wonders and immense gravitational forces. My mission to deploy new sensor arrays. These arrays would peer into a black hole's heart, or as close as we dared venture. The anticipation was truly electric. A palpable hum filled the entire ship. We trained for years for this moment. Every scenario was meticulously simulated, yet space always holds its surprises. I remember staring at the star charts. They showed our path, a thin line across an ocean of black. We were explorers, modern-day Magellans of the cosmos, seeking not new lands but new understanding. The launch was smooth, a controlled burn. Earth shrank behind us, a beautiful blue marble. It faded into the star-dusted canvas. Our solar system became a memory then, just distant points of faint light. We were truly alone out there, or so it felt. Little did I know what awaited. Weeks turned into months in transit. The Stardust Drifter performed flawlessly. Its fusion engines hummed a steady song, a lullaby for the long voyage. We passed nebulae, vibrant clouds of gas, stellar nurseries birthing new suns. Each view was a masterpiece, painted by gravity and light. The universe displayed its awesome artistry. We were privileged, silent observers, witnessing creation on a grand scale. Our destination grew closer, the Cygnus X1 region. It wasn't just the famous black hole. Our focus was a smaller companion, a suspected micro-singularity, dubbed the Crimson Anomaly by astronomers. Its gravitational lensing was unusual. It bent light in strange ways, not quite matching our existing models. This was the puzzle we came to solve, or at least to gather more clues. The region was dense with radiation. Our ship's shields glowed faintly, protecting us from cosmic rays. We navigated carefully through fields of stellar debris, remnants of ancient supernovae, each particle a tiny bullet. The void is not truly empty, it is filled with whispers of past events, violent, energetic, and transformative. As we neared the Crimson Anomaly, a sense of profound unease settled. The ship's sensors began to register higher than expected energy readings, fluctuations that defied easy explanation. The universe was preparing a lesson. We deployed the advanced sensor arrays. They unfurled like metallic flowers, reaching out towards the anomaly. Data began to stream back: numbers, graphs, complex energy patterns. The science team was ecstatic, then puzzled, then deeply concerned. The readings were stable, yet impossible. They contradicted established singularity models, specifically the models of infinite density. This was not what we expected. The event horizon was not smooth. It appeared to shimmer, to fluctuate, almost like a heat haze. But this was gravity, not heat. Information, or what seemed like it, was leaking from its boundary. Tiny, almost imperceptible packets of energy. Current theory said this was impossible. Nothing escapes a black hole, not even light. Yet our sensors were insistent. They were calibrated perfectly. The data was undeniable. I remember the silence on the bridge, broken only by the soft hum of computers. Everyone stared at the main screen. It displayed the anomaly's profile. The data streams painted a new picture, one that physics had not foreseen. It was a moment of profound discovery and profound intellectual discomfort. The cosmos had a secret. So what is a singularity? Imagine a star, a really, really big star, much bigger than our sun. When it runs out of fuel, it collapses under its own gravity. Boom! A supernova explosion happens. But the core might remain. If it's massive enough, it keeps collapsing. Gravity pulls everything inwards, tighter and tighter, until it becomes incredibly small and incredibly dense. This is a black hole. At the very center of a black hole, theory predicts a singularity, a point with zero volume but with infinite density. Think about that. All that mass squeezed into nothing, an infinitely sharp point of space-time. Our laws of physics break down there. General relativity, Einstein's theory of gravity, it tells us singularities should exist. The Big Bang theory also suggests the universe itself began from a singularity, a point of infinite energy. These singularities are mathematical constructs. They arise from our equations when we push gravity to its limits. They are places where space-time curves infinitely, where our understanding stops. We cannot directly see a singularity. It's hidden behind an event horizon, the point of no return. Cross it and you can't escape. That's why black holes are black. Our observations of the Crimson Anomaly, they pointed to this very idea. The infinite part was the problem. The data showed a core, not a point but a tiny region, extremely dense, yes, but finite in size, and crucially, it seemed to radiate. Not Hawking radiation, which is different. This was something else. A subtle leakage of structured energy, almost like information. Singularity theory assumes perfect collapse to an infinitely small point, but what if something stops it before it reaches true infinity? Perhaps quantum mechanics steps in, the physics of the very small. It might prevent infinite compression, creating a quantum core instead. Not a singularity, but a Planck star, or something similar we haven't imagined. Our sensors picked up its signature, a faint whisper from the edge. This changes everything about black holes. If the core is not infinite, then information might not be truly lost. The universe might not like infinities. The implications were staggering. Sir Roger Penrose's work was monumental. His singularity theorems are pillars of physics. They mathematically proved that singularities are inevitable under general relativity, given certain conditions of course, like the presence of trapped surfaces from which light cannot escape. His work earned him a Nobel Prize, and rightly so. It shaped our view of black holes and the universe's origins for decades. But our findings suggested a nuance. Perhaps general relativity is incomplete at those extreme scales and densities. It might need a quantum partner, a theory of quantum gravity. This is the holy grail of physics, a theory to unite the very big with the very small. What if this quantum gravity smears out the singularity, prevents it from becoming truly infinite? This would not invalidate Penrose's work, but it would refine its domain. The flaw we found was not in the maths, not in general relativity itself, but in its application to the extreme, where quantum effects must dominate. Our data hinted at this new regime, a place where gravity and quantum dance in ways we don't yet understand. The Crimson Anomaly was our window into this new, uncharted physics. It showed a limit to infinite density, a boundary set by nature itself. The implications are vast. If singularities aren't infinite, the information loss paradox dissolves. Information is transformed and re-emitted. Quantum mechanics insists information is never lost. A huge puzzle piece clicks into place. Then there's the Big Bang. Could the initial singularity be finite too? This could change our models of the universe's first moments. This journey, this discovery, it highlights something crucial. The role of observation in science. Theories are beautiful, elegant things, mathematical poetry if you will, but they must match reality. They must be tested against the universe. And when they fall short, we must be brave enough to say so, brave enough to seek new explanations, even if it means questioning giants like Einstein or Penrose. Our mission to the Crimson Anomaly, it was a testament to human curiosity, that insatiable desire to know, to understand our place in the cosmos. We build incredible machines like the Stardust Drifter. We hurl them across vast distances, all to gather a few photons, a few bits of data that might rewrite our textbooks, that might change our perspective on everything we thought we knew. It is a noble, vital pursuit. Science is a process of refinement. It is not about being right all the time. It is about getting less wrong, about approaching truth step by step. Each discovery, big or small, adds to our collective knowledge. The flaw in singularity theory is not a failure of past science, it is a triumph of the scientific method. So, where do we go from here? The discovery near Cygnus X1. It has opened a Pandora's box full of new questions and exciting research avenues. Theoretical physicists are already buzzing, crafting new models, new mathematics, trying to incorporate these findings into a more complete picture of gravity and the quantum world. The challenge is immense. The potential rewards, even greater. Future space missions will be vital. We need more data from other black hole candidates, from regions of extreme gravity. We need to build better sensors, more sensitive instruments to probe these cosmic enigmas, perhaps even detect gravitational waves from these fuzzy cores. The next generation of explorers will venture even further, pushing the frontiers of knowledge with courage and ingenuity. This is an ongoing adventure. We stand on the cusp of a new era in physics, an era where quantum gravity might finally become an experimental science, not just a theoretical dream. The universe has given us a clue, a significant, tantalizing clue. It is our task to follow it, wherever it may lead, even if it challenges our most cherished ideas. That is the path to deeper insight. That is how we truly learn. The cosmos awaits our questions. It is vast, mysterious, and beautiful, and it is full of surprises.